All right, today we're going to look at gas stoichiometry. This is yet another thing that you have learned, but it's really important to go over. This is where we start to develop our ability to go from one compound to another, not just limited to solids and solutions, like in Chapter 4, but now we can also deal with gases as well. So on your note sheet, you have a layout that should look extremely familiar to you. This should be something that you can see the flow between moles and particles and grams and now volume extremely well. So if I fill this in, this is what it should look like. We have our grams in the upper left, we have our particles in the upper right, we have our liters in the bottom, and we have our moles in the middle. And the thing that links them all together is our mole ratio. That is the coefficient in our balance equation. So you should be filling that in as we're talking. Okay, to add to that, and I think it's really important just to make sure that we've emphasized this, a couple major things is what are we using in the middle? I just want to make sure we're all on the same page. Right, I'm going to be using my molar mass there. There I am. I use Avogadro's number. In between liters, add STP. We learned before that any gas at STP, meaning at 0 degrees Celsius and 1 ATM. And as we spoke yesterday, 1 ATM can be 101.3 kPa, 760 torr, 760 millimeters mercury, or 14.7 psi. It will always be 22.4 liters. So the only value that changes from one unit to another, or one label to another, is mass. If it's particles, it's always Avogadro's number, and if it's volume, add STP, it's always 22.4 liters. Okay? If I'm going too fast, you can definitely pause this right now. But we are going to move on. So let's take a look at one of our problems here. And the first one is how many liters of CO2 are produced when 75.2 grams of C3H8, which is propane, in like a gas grill, reacts with excess O2 at STP. A couple important things on here. But first, let's label what we don't know. So here's my balance equation above. I already balanced it for you. I have 75.2 grams of my propane. I have excess O2, so that means I don't have to worry about this being a limiting reactant problem, which is really great. And then I want to have liters of CO2. And the big key with that is that this is all at STP. So why is that important? Because I am starting at grams of my compound. I can move down to moles. I can go and convert back. See, let's be clear on this. This is my propane. So my other compound is my CO2. And because it's at STP, I can travel through that row. I can utilize my 22.4 liters. So that's a 3-step T-chart, and let's set it up. Molar mass of propane is 44. I'm converting from propane to carbon dioxide, so I look at my mole ratios. For every one of these, I have 3 of those, so it's a 3 for 1. And now, you could be solving for a lot of things. If you're solving for mass, you put the molar mass of CO2 on the top. If you're solving for particles, you put 6.022 times 10 to the 23rd. But in this case, I'm solving for liters. It is a gas, and that's what it's asking for at STP. I'm solving with 22.4 liters. You calculate it all out, and you get 114.9 liters. If you want 3 sig figs, it'd be 115 liters. And that is a stoichiometry problem when at STP. All right. Again, pause it if you need a little extra time, but we will move on to the next problem. So, looking back at this, is sometimes you're not at STP, okay? Sometimes you need to take a detour. So what I mean by that is this road, these paths are blocked. You cannot take that road. It's like a toll booth, or again, like construction's going on because you are not at STP. So what we need to do is get from liters to moles. The only way to do that is by utilizing some of the variables that are associated with our gas, like our pressure, our volume, our temperature, and we can solve for moles. That'll get us on to the flow chart. If I'm on the flow chart and I want to get to liters, again, I have another roadblock, so I have to go on a detour. So that is, if I'm solving for volume now, I need to utilize the moles that I just found. That's my N, right? I'm going to take the temperature, and I'm going to take my pressure, and I can solve for volume. So what this is, it's a T-chart with an ideal gas law. So make sure you fill these in onto your flow chart in the beginning of your note sheet. So let's take a look at the next problem. I am using the same equation for all, just to make this a little simpler. So what mass of CO2 is produced? Okay, so I want to know mass if CH3 reacts at, and it's giving me some information. Now, you may not need to write this down, but I'm going to, just to show you what I'm thinking about. I have that temperature, I have that volume, right? So I have a pressure, I have a temperature, and I have a volume, okay? So we can kind of talk about where we're going with that. So I must be starting still with C3H8, and I must be ending with CO2 because that's the question. Let's talk about what I have. I want mass, okay, and let's look. I have a pressure, I have a temperature, and I have a volume. We're looking at grams, particles, moles, and volume. The only one that links is volume. So that means I must be starting here. Okay, so I am not at STP. Again, STP would have to be, in this case, for it to be STP, I'd have to have 101.3 kPa, and I'd have to have 0 degrees Celsius. That's not the case. So I need to take a detour, then I need to go this route, and then I need to go that route. So the only way to get there is using N equals PV over RT. So that's how I'm going to start it. This is the notation I'd like you to use. So I'm going to define, what my moles are. I'm solving for moles of propane. Please write it like that, as far left as you can, or just right there. Okay, so I am solving for PV over RT. Sometimes it's not a bad idea to write it out first. And now I need to place it in there. So 96.7 kPa. My volume, we learned this yesterday. Your gas constant has some specific units that it has to have, and one of them is liters. So I have 950 milliliters, so that's 0.95 liters. My R value has to correspond to the what? The pressure. So on your sheet, you're going to have a 0.0821. That's your ATMs, but you need the kPa. So as we talked about yesterday, you could take the 0.0821 and multiply by 101.3, or you could have this memorized. 8.314. I'm going to give you a pass on the units. Just write it out. And then lastly, I do need to have my temperature in Kelvin. So you got to make sure that you add 273 to all temperatures when they're in Celsius. So I get 0.0378 moles of propane. Great. Now I am currently right there. So now I need to do 2 more steps. So now I simply take my value, and actually if you had this way to the left, you could have taken your answer and then just started a T-chart on it, but that's okay. I'm going to do my mole ratio. So for every 3 CO2s, I have 1 propane. And now, I put CO2 right there. And last time we were looking for volume. This time we are looking for mass. So I add a carbon and 2 oxygens, and it happens to be 44 grams. I multiply that out, and I approximately get nearly 5 grams of carbon dioxide. So this is a great example of a gas stoichiometry problem that is not at STP. Again, you need to pause it. To do so, we will move on to the next problem. Once again, we're using the same equation, so let's take a look at what we have. It says if 4.75 times 10 to the 23rd particles of oxygen reacts, how many liters of carbon dioxide would be produced if the reaction occurs at 680 torr and 25 degrees Celsius? Again, organize your information. So I have that many particles. It says how many liters of carbon dioxide would be produced, and then in general, I'm just going to write this right here. I have 680 torr. I kind of just put it under the reaction arrow. I don't quite know where this goes at the moment. And 25 degrees. It's not associated necessarily with one thing, so I will figure out what I'm going to do with it. So again, let's take a look at what we have. So in this case, I'm given oxygen, and I'm asking for CO2 yet again. So let's take a look at where we are. I am given particles of my oxygen, and it looks like I want liters of my CO2. So let's take a look at the route. I'm going to go towards moles, mole ratio, and oh, nope, that doesn't exist. I'm not at STP, so that can't be. I must have to take a detour. So what does that look like? I got to solve for V, so that's nRT over P. So this time what it looks like, the last one we had to do the ideal gas law first, then a T-chart. In this case, it looks like we have to do a T-chart, then the ideal gas law. So it looks to me like we have 2 steps in the beginning. So let's take a look at how that will work. Take my particles, particles go down, so I'm using Avogadro's number. Over 1 mole. Right, I'm right there. Now I gotta do the mole ratio. So for every 5 moles of O2, I have 3 moles of CO2. I run out of room a little bit, so I'm going to write it down here. Okay, what's the big deal on that? Well, let's take a look at this for a second. I couldn't have multiplied it by 22.4 because I'm not at STP. So, what is this? This is my N, correct? This is my P, and this is my T. Perfect. At P, T, and N, I can solve for V. So again, this is how I'd like you to finish this and making it as label-friendly as possible, is that we're going to solve for the volume of CO2. So I'm going to plug them all in. I need to look at my pressure. I have 680 torr. I'll move this over a little bit. So again, you could change that into ATMs so your R value works better, or you could memorize your R value. So if you were using torr, your R value would be 62.4 with 680 torr. And then finally, I have a temperature, 25 degrees is 298 Kelvin. So I slide this all over because I just ran out of room. I get 12.9 liters of CO2. So that is gas stoichiometry. Most of the problems you'll be able to clearly tell immediately if you're at STP or not. I try to go out of the way to kind of show that. But I do want to go over one problem that's a little more unique. It may or may not actually deal with any gas stoichiometry, but I want to make sure that you understand how to do it moving on. So if we take a look at number 7, gas is 2. It says as the density of a gas was measured at 10 degrees, 805 torr, and found to be 3.21 grams per liter. Calculate the molar mass of the gas. What is the gas? Okay, right away, I know this is not stoichiometry though, because I'm not asking about one compound to another compound. So this is a straight off gas law, okay? So let's talk about that for a second. I was given temperature. I was given pressure. You don't have to write any of this, just illustrating it. I was given density. And it's asking for the molar mass. And then what is the gas? You don't have to have this memorized, but if we do a little manipulation quickly, take our ideal gas law. This is a bit of a stretch. If you take moles and you put mass over molar mass, what that does is molar mass is grams per mole, and you have mole on the top. So basically, mass would be canceled out. Moles are on the denominator of the denominator, and you're not really altering it. That's besides the point. If you rearrange this, what you get is this equation. I know that looks a little funky. I just flipped these two around, okay? But this right here, mass over volume, is density. So when it's all said and done, this is the equation that we're looking for. You probably recognize that from last year. Molar mass equals dirt over P. You cover your P with dirt. So I can plug this in using my numbers right now. I want to know the molar mass of this equation. So it's still important to have the right units. So that's my density. My R value needs to match up again with my P, so I have torr. So I'm going to do 62.4. My temperature is 10, so plus 273. 283, and then my pressure is 805 torr. I calculate that out, and I get 70.4 grams per mole. It asks what element is that. You have two choices. You could look at the periodic table, and gallium weighs about 70. It's 69.7 grams per mole. But the problem is it's not a gas. It is not a gas. So your second thought should be, is it diatomic? We have 7 gases that are diatomic. So if you split 70.4 in half, that's roughly 35 with a little change. Hey, that's chlorine. So the compound that we're looking for must be Cl2. So couple that with our stoichiometry in STP, not at STP, and then utilizing density and molarity. Hopefully that'll get you going. You have the rest of the period to be working on your gases 2 or finishing up gases 1.